Einstein might be wrong. All hell broke loose in the physics community. It means that time travel could become commonplace, because as you approach the speed of light, time slows down.
Interstellar space travel has always been a source of fascination, fueling the dreams of every young child within us and serving as a prominent theme in science fiction stories. It represents a daring journey into unexplored realms, defying boundaries in an extraordinary manner. As our technology continues to advance, the inevitable question arises: is it possible for us to ever venture out and establish colonies among the stars? And if achieving that ambitious dream proves to be too far-fetched, could we at least send space probes to distant planets and learn from their observations? The truth is that from a technical standpoint, interstellar travel and exploration are not inherently prohibited by the laws of physics. There is no specific law that outright forbids it. However, this doesn't mean it is an easy feat to accomplish. But despite the fact that we have yet to find definitive answers to these challenges, recent progress, facilitated by NASA's vigilant detection systems, suggests that the final frontier may be more within our grasp than ever before. Has NASA developed a technology capable of travelling at the speed of light? Is the concept of warp speed merely a fanciful invention of science fiction, or is it a conceivable reality? Let us embark on a quest to uncover the truth. Einstein's special theory of relativity provides the foundation for our understanding of time and the speed at which objects can move. According to this theory, the speed of light serves as the ultimate speed limit in the universe, beyond which nothing can travel faster. This fundamental limit applies to every object in motion throughout the cosmos. The incredible speed of light allows it to traverse vast distances in mere moments. For instance, light can travel from Earth to the Moon in just over a second, and it can streak across the entire span from Los Angeles to New York City in less time than it takes to blink. However, when it comes to reaching Proxima Centauri, the star closest to Earth, the story is entirely different. Proxima Centauri is located a staggering 4.25 light-years away from our planet. Even the fastest spacecraft ever built, the Parker Solar Probe, pales in comparison to the vast distances of interstellar travel. Currently in orbit, this probe achieves a peak speed of 700,000 kilometers per hour. At this remarkable speed, it would take a mere 20 seconds to travel from Los Angeles to New York City. However, when contemplating a journey to the nearest neighbouring solar system to Earth, the Parker Solar Probe would require approximately 6,633 years. Currently, there are 5 spacecraft from Earth venturing into interstellar space: the New Horizons spacecraft, the 2 Pioneer spacecraft, and the 2 Voyager spacecraft. These remarkable explorers are travelling at speeds of tens of thousands of miles per hour, which may sound impressive. However, they are not heading towards any specific star, as their missions were designed to explore planets within our solar system. If any of these spacecrafts were aimed at Proxima Centauri, it would still take around 80,000 years for them to reach their destination. Traditional rockets, unfortunately, are not suitable for interstellar travel due to their limited speed. If humanity ever hopes to travel conveniently between stars, we will need to achieve speeds faster than that of light. At present, faster than light travel remains a concept confined to the realm of science fiction. In fictional works like Interstellar and Thor, wormholes provide characters with instant travel between solar systems, while Star Trek introduces the idea of warp drive technology, familiar to fans of the franchise. When the writers of Star Trek were developing the series, they faced a significant challenge. They wanted to create a space opera, a type of science fiction story set in space, spanning multiple galaxies and millions of light years. However, they also aimed to adhere to the principles of physics as much as possible. The main obstacle they encountered was the immense timescales involved in intergalactic travel, even at the speed of light. For example, travelling from Earth to the centre of our galaxy would take approximately 25,000 years at light speed. To maintain an engaging and dynamic narrative, the warp speed concept was introduced in Star Trek, allowing the Enterprise and its crew to travel faster than the speed of light. The warp drive functions by combining matter and antimatter in a fusion reaction facilitated by dilithium crystals, generating the tremendous power needed to warp space-time and propel the ship at faster-than-light speeds. In the Star Trek series, velocity is measured in warp factors, with warp factor 8 being the equivalent of 512 times the speed of light, following a cubic progression. However, even at these velocities, starships would not be able to travel as quickly as they appear on television. In reality, the writers of the show allowed the Enterprise to reach its destinations as swiftly as necessary for storytelling purposes. In later iterations of the series, such as Star Trek The Next Generation, the warp speed scale was recalibrated. Under the new scale, a starship could cover the distance from Earth to Alpha Centauri in approximately 37 hours at warp factor 8, providing a glimpse into the vast distances between stars. However, in 1994, physicist Miguel Alcubierre put forward a theory that challenged the conventional notion of traveling faster than light. Instead of moving a spaceship, Alcubierre promised a concept where space itself could be manipulated to achieve faster-than-light travel. The concept involved distorting the fabric of space-time to create a bubble around the spaceship. Although this approach required immense amounts of energy, once the bubble was formed, it could move independently of the rest of the universe, surpassing the speed of light. According to Alcubierre's theory, it was mathematically possible to compress space-time in front of the spacecraft while expanding it back within the boundaries of general relativity. To illustrate this concept, imagine 2 points 33 feet apart. If you could move at a speed of 1 meter per second, it would take you 10 seconds to travel from point A to point B. However, suppose you could somehow decrease the distance between point A and point B to just 1 meter. In that case, by traveling at your maximum speed of 1 meter per second through space-time, you would reach point B in less than a second. Since you wouldn't be surpassing the speed of light in the surrounding space, this approach theoretically would not violate the principles of relativity. Alcubierre's proposal suggested that a warp drive, similar to the one depicted in Star Trek, could be theoretically feasible. However, there was one significant drawback to Alcubierre's concept. It required negative energy or negative mass. The warp drive would envelop the spaceship in a bubble of flat space-time and manipulate space-time to shorten distances. To achieve this, either a ring of negative energy density or hypothetical negative mass would be necessary. Negative energy was the more plausible option, as physicists have not observed negative mass. A warp drive would rely on a substantial mass to tip the balance toward negative energy by trapping one particle with the mass. The imbalance caused by the appearance of an electron and an anti-electron near the warp drive would result in a decrease in energy density, which the warp drive could utilize to create the space-time bubble. However, generating enough negative energy would require an immense amount of matter. According to Alcubierre, a warp drive with a 100-meter bubble would necessitate the mass of the entire observable universe. In 1999, a scientist demonstrated by increasing the volume inside the bubble while maintaining a constant surface area, the energy requirements could be dramatically reduced to approximately the mass of the Sun. Although this improvement was significant, it still remained far beyond what was practically achievable. Furthermore, NASA engineer Dr. David Burns has been working on a potential solution to the challenge of achieving high-speed travel without the use of fuel. In his design, Burns proposes an engine that could travel up to 99% the speed of light. He uses a thought experiment involving a box with a weight hanging by a thread, 2 springs at its ends, and the weight shifting back and forth to illustrate his concept. If this box were placed in a vacuum-like space, the weight would appear motionless, creating a stabilized effect. However, the entire box would tremble, indicating underlying movement. Normally, the box would experience slight vibrations even when stationary. However, if the weight's mass were to increase more in one direction than the other, it would generate a stronger force and a greater push in that direction. According to the principle of conservation of momentum, the overall momentum of a system remains constant regardless of external influences. Although achieving full thrust in these conditions might be challenging, a potential crack in special relativity offers a glimmer of hope. According to special relativity, objects become heavier as they approach the speed of light. In theory, ions within a loop could move faster at one end and slower at the other. Replacing the weight in the box with ions and utilising a helical design resembling a dilated spring, Burns's concept, known as the Helix Engine, accelerates ions within the loop to relativistic speeds before manipulating their velocity to slightly modify their mass. The engine creates thrust by alternately moving ions in the direction of motion. Importantly, the engine relies solely on the movement of ions along a vacuum line, controlled by magnetic and electric fields, without the need for any other moving components. While this idea holds great promise in principle, there are several significant practical challenges to address. The helical chamber would need to be exceptionally large, measuring 656 feet in length and 40 feet in diameter. To generate 1 Newton of thrust, it would require 165 megawatts of energy, equivalent to the output of a power plant to accelerate a mass moving at 1 kilogram per second squared. Consequently, despite the significant input, the resulting output is extremely small, making the process highly inefficient. However, in the vastness of space, with sufficient time and power, this engine could potentially operate near the speed of light, according to Burns's proposal. Can humanity realistically attain speeds equal to or surpassing the speed of light? Share your thoughts in the comments section.